I'm going to mostly talk about some highly phenomenological subjects which are related to the gamma ray burst phenomena. So as you already probably heard about this many times at various places, this subject has been a very interesting and exciting subject for many reasons. And so I'm not going to actually cover the entire field, and I don't think I have much time, but I want to actually emphasize just a few things in this field, which is to me related to actually a series of works I've been doing in the last several years. First of all, I'm going to mostly talk about gamma ray bursts generated by pulsars. So as we already were told by many speakers, pulsars and black holes are in many respects share some similarities. For example, a given pulsar would be given a rotation with a strong field, and a black hole could be equally strong in its magnetic field, although it's not self-generated. In a sense, magnetic field cannot be due to the black hole itself. It has to have some sort of a plasma around it. So most of the phenomena we have to describe in trying to build a model for gamma ray burst in the case of pulsar is similarly related to the black hole physics. There is one fundamental difference. That is, in pulsar's case, we can actually make all these numbers, time scales, energies, and things like that in place without resorting to any actually outstanding uncertainties. We already know what pulsars are. We already know actually what pulsars can do, and we already know actually what plasmas could do around pulsars and black holes. So the reason actually I'm talking about pulsars is because of the three reasons I listed down here. Before that, the talk I'm going to give you today is based on the works that I've been doing with various collaborators of mine listed here. Chungmi Kim, who's a research student at Ihwa, and Jungman Yang, who gave a talk yesterday here, and Josh Grindley, and he's mostly working with me on the connections between millisecond pulsars and the gamma ray burst. And Craig Wheeler, Peter Weflick, and Lifan Wang, they're actually working with me on gamma ray burst supernova connection. And Eric Blackman, who's at Caltech, who's doing actually most of the theoretical works on pulsars with me these days. So with due credits given to them, I'm just going to summarize what actually issues and developments I'm going to focus on today. These days, actually, people talk about gamma ray burst as phenomena related to massive stars. Massive stars being as massive as like a few to probably tens of solar masses. The reason actually they relate gamma ray burst phenomena to massive stars is because massive stars produce relatively massive remnants. That is to say, black holes and neutron stars. So pulsars, as we know, are produced or remnants of some massive stellar evolution. So if you have massive stars forming in all the universe or relatively recent universe, you can expect that actually these pulsars would be related to rapid star formation region, because massive stars would evolve on a time scale less than probably a few tens of millions of years. So these stars would be correlated in position and time with whatever activities associated with in stellar evolution. So normally what they do in phenomenological studies of gamma ray burst is to relate directly star formation rate to gamma ray burst rate, because there will be essentially on cosmological time scale, there will be no time gap between the gamma ray burst explosion and the star formation. Tens of millions of years is essentially nothing compared to the cosmological history. And then the most exciting, one of the most exciting discoveries in recent gamma ray burst study history is the claim, yet to be proven 100% at the 100% level, that the gamma ray burst might be correlated with supernovae. It's an exciting story because we, in the last decade or so, argued very strongly that gamma ray bursts cannot be coming from supernovae, because gamma ray bursts require much higher energies than supernovae. But now actually with this, although not so complete or final suggestion that gamma ray bursts are, at least some of them, are connected to supernovae, we might have to reconsider what kind of energies we need in explaining gamma ray burst phenomena. And the third thing is related to actually first and second. If you argue that some of the gamma ray bursts are coming from pulsars, or at least actually energetically not so favorable sites, like black holes with not so strong fields or not so strong spins, as we already will know, then you have to consider whether the gamma ray bursts detected have anything to do with the isotropic luminosity. That is to say, if the jets or outflows are strongly beamed towards certain directions, we might actually see these bursts as energetic as we observe, but they may not be actually such a strong catastrophic event. So what I'm going to say is that actually essentially you can generate this kind of gamma ray burst-like phenomena without requiring 10 to the 51 or 50 erg per second kind of luminosity in the end. You might need only just 10 to the 47 or 48, which is comfortably within the range of supernova physics. So that's what I'm going to say. But physically, what all these issues mean is unclear. The reason is supernovae are different from gamma ray bursts in many reasons. First, supernovae have a lot of germs flying around. So if you want to make gamma rays have to escape from this emission region without being blocked by this dense material. So gamma ray bursts traditionally have required some region free of this baryons, so what they call is baryon contamination. But supernovae are the worst kind of output you want to consider for gamma ray burst production. And second, if you want to have gamma ray bursts, you want to have actually a lot of energy still in gamma ray range. But supernovae are known to produce most of its energy somewhere not in the gamma ray range, as you'll know. So we have to consider some physical channels through which gamma ray bursts are produced, as well as actually supernovae explode. And then, while doing so, we have to have actually some pulsar generation mechanism or black hole generation mechanism. But I don't think actually I know much about actually how the black holes form from supernovae, so I'll actually concentrate on millisecond pulsar kind of formation, especially the pulsars with rotation period of milliseconds. The reason is simple. If you do not have pulsars spinning as fast as with a period of milliseconds, you will not have enough rotation energy to power the gamma ray burst. And so, why is millisecond pulsar so interesting? First of all, time scale is just right. Millisecond is a very interesting time scale for gamma ray bursts. Gamma ray bursts are actually a phenomena with the total duration of events ranging from milliseconds to hundreds of seconds. So it may be a very heterogeneous group of events, but at least the short gamma ray bursts are characteristic of actually this kind of time scale, which happen to be the millisecond pulsar time scale. Energy is about right. If you actually believe that the supernova energy, total supernova energy, is up to actually 10 to the 50, including all the energies coming in the neutrinos, the energy coming from the millisecond pulsar generation during the supernova collapse would be about right. And also, pulsars are known to produce beamed emission, and at least in radio. So if you believe in that energy generation in pulsars has something to do with the beaming, then actually pulsar is a very good one, already known to have some sort of a beaming going on. So that's mostly what I'm going to talk about, and then I'm going to mix at various stages the conventional supernova picture with the less conventional accretion-induced collapse. That is, white dwarfs collapse to neutron stars by accreting mass, thereby going over the threshold. So in this case, by accretion-induced collapse, AIC, I mean the explosionless or non-explosive collapse of a white dwarf to neutron star. But essentially the energetics is the same. So what is accretion-induced collapse, which I'm going to actually relate it to the core collapse of supernovae, or we have been trying to do that. So accretion-induced collapse is a process during which a white dwarf, which is accreting from a secondary star, collapses to neutron star. It's not a new subject. We have been talking about this, although there is not a single evidence that this process occurs in the universe. So what people actually half-jokingly argue is that gamma ray bursts are the accretion-induced collapse events. We haven't seen them because we didn't know actually what these are. But now, if you somehow connect the accretion-induced collapse events to gamma ray bursts, you might be able to say that actually what we have detected in terms of gamma ray bursts are the accretion-induced collapse events. So what is it? What happens is you just have a just ordinary, but some sort of a more massive white dwarf around at least 1.3 or even higher solar mass masses. And then you actually have a secondary star around it. And then the mass accretes from the secondary star to the primary. In this case, it's a white dwarf. And if the mass approaches close to 1.4 solar mass, then white dwarf will reach this critical Chandrasekhar limit, and it will not support itself against the gravity. Once that happens, you expect that actually the size of a white dwarf will collapse into a size of neutron star. But one critical quantity we have to worry about is actually the required accretion rate, that is the mass flow rate into the white dwarf, has to be very high. So high that actually one normally do not think this kind of accretion rate in binary systems. In terms of a definite number, I just chose 5 times 10 to the minus 5 solar mass per year, which is pretty high. And now, if you actually consider a white dwarf with a characteristic set of numbers, that is the moment of inertia of a white dwarf, I sub WD, that's about 10 to the 51, which is a number we normally associate with a white dwarf, and the radius of white dwarf about 10 to the 9 centimeter, and the rotational frequency of white dwarf, which is, in this case, I took 10 to the minus 2, which is very high. So if you give this kind of white dwarf about 10 to the 9 Gauss, then after the collapse, under the assumption that the angular momentum is not going to be lost while collapsing, so angular momentum conservation, and the magnetic flux is frozen into the plasma, then what you get after collapse into a neutron star is going to be 10 to the 15 Gauss, 10 to the 45 moment of inertia, 10 to the 6 centimeter radius, and 10 to the 4 angular rotational frequency. So this is what we expect. But there's one problem here. We have never seen any white dwarf with a magnetic field as strong as 10 to the 9 Gauss. But as you will know, without achieving 10 to the 15 Gauss, pulsars will not be interesting for gamma ray burst emitters. And there's not a good evidence that most of the white dwarfs, at least when they initially began, have rotational frequencies as high as 10 to the minus 2. So comparing that to gamma ray burst, what do we require? This is the same old number you've seen many times in many papers and talks. Gamma ray bursts are basically energetically about 10 to the 51 erg per second event, assuming that energy generation is isotropic, emission is isotropic, which depends on, of course, the cosmology, the redshift of the event, and the Hubble constant and things like that. But it's more or less a solid number. And another headache actually in gamma ray burst is actually time scale. Why is the time scale so widely varying? It could be as short as actually 0.01 second, could be as long as actually up to 1,000 seconds. Why is this time scale so different? That's been a main problem in this field. So if you have a pulsar, before going into that, I want to actually emphasize one fact. If you actually allow the source evolution of gamma ray burst, which mimics the star formation rate, what do you expect statistically? You don't expect anything. The detected gamma ray burst number at about now 2,000, and it's approaching 3,000 pretty soon. But these gamma ray bursts do not actually tell you whether star formation rate is statistically supported or not. So it's at the level of actually 2.5 sigma level. That's what we found, at least. And is there any signature for beaming? No. Beaming you expect actually is something very complicated, but in terms of statistical signatures, beaming only induces the luminosity function because the beam directed towards you would appear very bright, directed away from you, away from the line of sight, would appear less bright. So it induces an apparent luminosity distribution. But that kind of induced luminosity function, apparent luminosity function, doesn't affect the statistical signatures in gamma ray bursts. So unfortunately, at the level of 2,000 gamma ray bursts, you don't expect more than 2.5 sigma or so signatures in this. But I have something more to say, but it's rather involved, so I'm not going to say this. The reason I brought this issue up was because in the end, you might want to actually prove this or disprove this assertion that gamma ray bursts are beam radiation emission from pulsars. You sooner or later have to resort to some kind of statistical arguments, but that's just plainly impossible at this stage. So what do we have from millisecond pulsars? It's if you want to go into details, this subject would be very complicated. But basically, at the level of just energetics and time scale, it's very simple. From millisecond pulsars, you expect only essentially two channels of energy emission. One is gravitational radiation emission, when the pulsars develop non-polarizable moment. That is to say, it rotates with an asymmetric shape. So triaxial shape would be a good example. In that case, you expect up to well over, actually 10 to the 50 or 51 ohm per second, but in an invisible form. It's a gravitational wave, so you wouldn't detect them. But it all depends on this parameter epsilon here. Epsilon is actually how distorted the star is from the perfectly spherical shape. And another channel would be electrodynamic and electromagnetic radiation. Normally we assume dipole, but we don't know whether the pulsar magnetic field is dipole. Although it's not really entirely crazy, but the magnetic fields around pulsars are not proven to be dipole. But if you take a dipole number, then the luminosity would be about 10 to the 50 to 51, depending on the magnetic field strength. So as I told you before, the required magnetic field and the rotation are 10 to the 15 and 10 to the 4, which are extreme numbers even for pulsars. So if you actually want to talk about time scales, gravitational radiation emission time scale, T sub GW here, is about right. 3 times 10 to the minus 3, which is going to be about the shortest time scale you expect in this kind of pulsar system. And then there is electromagnetic time scale, which is unfortunately very long if you write it this way. I intentionally wrote this way because I chose a number for the magnetic field of 10 to the 12 Gauss rather than 10 to the 15 Gauss. If you put in 10 to the 15 Gauss here, you will reduce the number substantially, which falls right into the observed gamma ray burst duration range. But the reason I wrote in this way is clear, it lacks transparency. So, is gravitational radiation relevant for gamma ray bursts? Yes and no. Gravitational radiation itself has nothing to do with the detected energy in gamma ray bursts. But it is interesting because pulsars still can spin down while emitting gravitational radiation and electromagnetic dipole radiation. So it spins down quite rapidly while emitting dipole radiation. But the overall time scale is controlled by gravitational radiation emission rather than the electrodynamic radiation. So it could spin down quickly with a lot of power, but most of the power could go into gravitational radiation. Only 1% or less of the energy of this enormous 10 to the 55 or per second luminosity would appear as gamma ray burst, gamma ray burst energy. So it's an interesting number. So when does this actually gravitational radiation emission happen? That is pretty clear because of the decades-old study by Chandrasekhar and the later elaborated on by many others. It's clear that the pulsars will emit gravitational radiation by distorting its shape into non-axisymmetric shape at a critical period. So if the period of a pulsar is shorter than this critical period, which is about millisecond here, you expect that gamma ray bursts would probably arise from this kind of rapidly rotating and wobbling millisecond pulsars. So what do you get from here? Very simple. If you have a pulsar rotating faster than the critical frequency or a period shorter than critical period, you expect the time scale of this spin down would be gravitational time scale. So gamma ray burst spin down, duration would be the spin down time scale on the gravitational radiation time scale, which is short. As short as actually a fraction of a second here, right here. And then the luminosity will be still in gamma rays given by electromagnetic radiation. And second, if the pulsars rotate slower, slightly slower than critical, then there will be no non-axisymmetric distortion. And then the electromagnetic time scale would be the time scale because gravitational radiation emission doesn't work. But still the luminosity will be the same. So I think it's just purely based on these simple numbers, originally strongly advocated by Vladimir Yusov, these numbers are still very interesting. And even more so because of the recent attempt to connect the gamma ray burst to supernovae. So what do we know about these millisecond pulsars without explosions? That's actually accretion-induced collapse, which I call. So normally this kind of explosionless, silent, electromagnetically silent collision is expected in a particular type of white dwarf, which is called oxygen neon magnesium white dwarf. This kind of collapse would be expected if the central density of the star exceeds certain critical density written in here, which is actually right density for magnesium in terms of the electron capture. So once the electron is all captured by magnesium, there is no electron-supported degeneracy. So the core will collapse. This will happen, as I said, at a pretty high accretion rate, but normally these accretion rates are not expected. So that's the reason why we might not see this kind of events very often. So once these events are progressing, what do we expect? We first have to expect what happens right before the collapse. Right before the collapse, you expect to have a white dwarf massive enough to collapse, but it's rotating rather slowly. So before this collapse happens, we have to specify what is the condition prior to collapse, because everything is conserved during collapse, which is happening on a gravitational dynamical time scale, which is short. So we assume that angular momentum is conserved and magnetic flux is conserved. So we have to specify that. But fortunately, we pretty much know actually how this white dwarf spin is evolving. That is, white dwarf is actually getting mass as well as angular momentum from accreting mass, and then it actually also gets torque from the plasma, which is connected, accreting plasma, which is connected to the star through magnetic field. So I'm not going to go into this detail, but essentially this equation tells you the mass accretion and the size change because of white dwarf's mass change. As the white dwarf's mass changes, radius changes. There is a well-known mass-radius relation in white dwarf cases. And you have actually this N, which is the torque acting between the accreting plasma and the star. So it's pretty much well-known standard thing. And white dwarf's magnetic field will respond to the size change by attempting to conserve its magnetic flux, so flux conservation. So if you do that, you pretty much know what will happen to the white dwarf while accreting a lot of mass. So the detailed calculations I'm not even go into, but just basically a very heuristic expression here is sufficient. That is, white dwarf right before the accretion-induced collapse will have about 10-second period. It depends on the white dwarf magnetic field strength and the mass accretion rate. But we already know what the mass accretion should be and what the magnetic field dependence is. So pretty much sure that actually has to be about 10 seconds or so. But this is subject to some other technical uncertainties, but I'm not going to talk about. If you actually let that kind of white dwarf collapse into neutron star, what do you expect? You expect about this kind of millisecond pulsar. That is to say, on top here, the millisecond pulsar's rotation frequency will be about 10 to the 4 if the magnetic field is about 10 to the 11. So the pre-collapse white dwarf will turn into a 10 to the 11 Gauss, 10 to the 4 Hertz frequency millisecond pulsar with a number here, uncertainty ranging from 2 to 6, the factor of 3 essentially. So I'm not going to explain this factor of 2 to 6, which unfortunately has some things to talk about. But basically what I can assure you is that actually this is a very solid correlation between the magnetic field and the milliseconds pulsar spin. Now you have a pulsar, millisecond pulsar, and you want to produce gamma ray bursts by essentially letting them use their rotational energy. How do you describe it? Unfortunately, this is another massive question. It's been worked on for many, many years, but I don't think actually there is any essential improvement because of the large dynamical range of these numerical calculations. But what we can do is to borrow the original calculation from Chandrasekhar modified by the strong magnetic field. That is, I'm not going to go into these equations, which is meaningless in this kind of talk. We just essentially have a pulsar with a three radii. Remember, it's a triaxial shape. So rotation axis is in the direction, one direction here, and 2 and 3 directions are perpendicular to the rotation axis. And these 3 radial extents of a star are different, so they are triaxial. So 1 is the rotational axis, 2 and 3 are directions perpendicular to the rotation axis. Then everything else in these equations describing how the star should respond to its spin down is described by these 2 equations. So here L's mean the ratio of 2 radii with respect to the size of the star along the rotation axis. And if you actually have this nonlinear differential equation, it's just simple to solve this. If you just solve it coupled with the magnetic field, because we want to know how the magnetic field also changes while the star is spinning up or spinning down. So what you have is actually a set of dynamical equations described for the star. But while the star changes its shape, essentially what happens is that a plane perpendicular to the rotation axis changes its effective area. So the magnetic flux threading the star in this plane will change. So if you allow the flux conservation, then what you have is the magnetic field strength change, because you said that actually there should not be any flux change. So it's exactly the same as in just area calculation. What you have to worry about is a triaxial shape. So if you do a little bit of manipulation, assuming that the magnetic field maintains a dipole shape, then what you get is essentially this expression here. That is, the magnetic moment along this one axis, this is the rotation axis, is mu star 1, which is actually a simple function of a geometric shape. And R bar is a sort of mean size of the star. So the geometric ratios of these, this is a geometric ratio of this dimensionless radii I defined in here, right here. So 2 to 1, 3 to 1 axis ratio. And then there is only one complication, that is the magnetic moment along the rotation axis is just completely specified by just accident, complete elliptical integral of second kind. So you actually have this expression so that as soon as you solve these 2 equations, you know how the magnetic moment changes. So after all doing this, it turns out that the electromagnetic power as the pulsar spins down doesn't change a lot by this geometric effect. Before doing these calculations, we had no idea, but after doing this, the effect arising from the changing effective cross-sectional area of a star is only at the level of factor of 2. So mostly the electrodynamic, electromagnetic power is affected by the spin down, as in ordinary calculation, without considering star's shape change.
Can I ask a question about that?
Yes.
When we include the small gravitational reflection, do you have that kind of potential because of exponential shape?
Actually, that's the question which I try to avoid. So actually, if you have this bad reaction from gravitational radiation, you're not guaranteed to have a homogeneous ellipsoid without any density structure. There could be actually some internal velocity structure too. Then you cannot actually describe this kind of shape with a homogeneous ellipsoid. It has to contain some other physics, which is what they call is a other spheroid structure, but we haven't done that. So bag reaction is important. So after just describing what happens to the magnetic moment of the star, you obviously can write down this expression. That is, electromagnetic luminosity, power, is just the magnetic moment defined along the rotation axis squared times the rotational frequency to the fourth, which is exactly the same expression as you expected. So the gravitational radiation timescale, which I defined or showed, and electromagnetic timescale are all in here. So if you just include this expression and then combine this with the, if you remember, the magnetic field to spin correlation, which I defined, if you remember that, then you can actually write down a single expression which is unique in this picture. That is here. So if you combine the top expression with this correlation between omega and B, then you eliminate 1, obviously. So what you have is a pretty obvious expression. That is, electromagnetic power always comes out as a number which depends only on the magnetic field or rotation. So electromagnetic power is 10 to the 44 erg per second times omega star over 10 to the 4 to the power of 3 halves. So what is this number? This is pretty small compared to the gamma ray burst number. So if you believe in nothing but this very classical picture of a white dwarf to neutron star collapse and then spin up and then spin down by gravitational radiation emission, you expect only about 10 to the 44 with a definite dependence of like this. And the spinning down will happen on a gravitational timescale. So what this means is that the electromagnetic radiation emission timescale is too long to be compared with the gamma ray burst emission timescale, which is only a few seconds, let's say. So we introduced a couple of years ago, and Professor Lee also talked about precession. So now if you have actually a certain beam shape which is well collimated, then binary systems could actually interact with each other. So this beam is not going to stay steady in space and time. It will be affected as the jet space, which is connected to the star, would be affected by the other things, secondary star, for example, in binary systems. So we expect that there will be a jet precession. So if the jet precession happens, then even if the beam is steady and emitting the radiation for a long time, the beam would actually sort of wobble out of and into the line of sight. So it could actually produce some apparent short time scale events with some various interesting variability properties. But I don't want to go into this detail, but there are at least the 3 well-known mechanisms which are listed in here, but I'm not going to talk about it. I don't have much time. So at least there is a mechanism which can actually prevent this kind of long time scale from being a problem for gamma ray burst emission mechanism. So if you actually, I'm not going to go into this detail, but if you actually demand that observed 1 second, 10 second duration has to be related to this kind of definite mechanism, then you have to have a very sharply beamed gamma ray burst. So that beam size has to have a very narrow width. So that translates into this kind of constraint. And again, if you have a beam, one ordinary objection to beam picture is that it will repeat itself. But it's not the case, because actually there are different precession mechanisms which will prevent the a repetition of the same kind of beaming coming into your line of sight. So that's not really a problem, as long as you have a certain constraints on the binary system parameters, which I wrote down in here. But I don't think it's particularly interesting for you at this point. So what happens once actually this emission happens? So electromagnetic dipole radiation is in the form of just pure Poynting flux. So it just flows out. It has nothing to do with a gamma ray burst in that form. So it has to convert itself to a gamma ray burst. So what we advocated was exactly what Vladimir Yusov has been arguing for. It's a very nice, well-defined picture, except the fact that if you have a lot of baryons moving around, this mechanism would fail. I'll explain it just briefly, which is a little bit involving. That is, if the Poynting flux flows out, then it's essentially an oscillating electric field flowing out. It has nothing to do with the dissipation. Gamma ray burst has to arise from dissipation of this pure wave form of energy. So what happens is that in this Yusuf's original picture, and due to actually earlier papers, but in this present form, this first, as far as I know, was written by Yusuf. That is, after actually this plasma coupled with these waves flow out, there's a certain radius at which the density becomes low enough that the current cannot be sustained. So once the current is not sustained, then you cannot maintain a perfect MHD-like condition. So something like a particle creation should happen. That happens exactly when the intrinsic plasma density falls below the classical Goldreich-Julian density. That's the density at which first the current, which is required to support this wave motion, is breaking. So you just cannot sustain that activity at this radius. In the parameters we just talked about, 10 to the 11 Gauss, 10 to the 4 for the spin frequency, you essentially have about 10 to the 12 centimeter. That's not far, but that's far enough from the center, that is about 10 to the 6 centimeter. So you will expect, in this case, a relatively baryon-free region where this picture is relevant. So I'm not going to go into details, but essentially in this picture, what happens is once this actually radius is reached, then there will be particle creation in terms of pair creation, electron and positron creation. And these electrons and positrons gyrate in magnetic field, and it produces synchrotron photons. And these synchrotron photons collide to themselves, their parent electrons and positrons. So it's a synchrotron componization process. So it's self-componizing synchrotron-produced photons, and in doing so, it reaches a very high energy, essentially about the energy of the electrons and positrons, which is about 10 to the 10 to the 20 hertz. That's about gamma rays. So I didn't even actually bother to write down the expressions, which is meaninglessly complicated in here. But what I can tell you is that the spectrum expected is characteristically at around the frequency of 10 to the 20, and its tail could be as high as at 10 to the 24. So it's about 1 MeV to 1,000 MeV range. So that's expected. Okay. So if you actually have gamma ray burst, then what happens is that this frequency here, synchrotron frequency here, has to be in the right range. That is to say, observe the 1 MeV range. But as I already said, this arises naturally. So what I wrote down in here is that the required gamma ray burst emission tells us that the pulsar has to have this kind of a relation. That is, the spin frequency has to be comparable to the magnetic field in this relation. So the gamma ray burst generation in this picture is never a problem. It just comes out naturally. Then I think there's an interesting question which I addressed with Josh Grindley. That is millisecond pulsar rate interesting in gamma ray burst rate? Actually, the answer is no. there's only one way to get out of here. That is, the millisecond pulsar observers have tried to estimate the millisecond pulsar birth rate. Pulsars spin down and then disappear as millisecond pulsars because it loses rotational speed. So what we expect is about the rate of 10 to the minus 5 per year per galaxy. That's based on the lifetime of detected the millisecond pulsars in our. We actually have compared that to gamma burst rate, assuming that gamma ray bursts are homogeneous, then you expect about 10 to the minus 6, a few times 10 to the minus 6. So rate is comparable, but it's not the same. But I think that there is a problem here. That is, this millisecond pulsar birth rate was based on the magnetic field strength of about a few times 10 to the 8 Gauss. But the kind of pulsars we are talking about is actually pulsars with 10 to the 11 Gauss. So their spin down time scale through electromagnetic radiation emission will be much shorter. So you actually have the millisecond pulsar birth rate, which is actually as large as this, but it could be actually even bigger. So if you compare that to the gamma ray burst rate, then there is one way out of this problem. That is, gamma ray bursts are intrinsically very sharply beamed. So you need a lot more gamma ray bursts than isotropic case because you detect only a certain fraction of it. Then you can compensate for that by assuming that the millisecond pulsars are born with 10 to the 11 Gauss. But we know that actually most of the pulsars we detect have magnetic fields less than 10 to the 10 Gauss. So what we argue eventually is that gamma ray bursts are arising, if they have to, arising from millisecond pulsars with intrinsically very different magnetic field strength than most of the ordinary millisecond pulsars. So I think it's a reasonable conclusion, but there's no way we can actually prove it at this point. So now actually I want to just finish with one interesting thought me and Eric Blackman has been advocating, but there are some problems which I hope I can address in a very short time. That is, if the pulsar spins very fast, then actually there is a competing mechanism for magnetic field amplification, not only just flux freezing through the contraction, but also the internal dynamo mechanism. So there are three critical frequencies based on what we already talked about. That is, stellar frequency, pulsar's frequency, and omega critical, which has something to do with the gravitational instability, and the dynamo frequency. So if the star rotates faster than a certain period, then internal dynamo would trigger in. So what happens is you have three cases. You have three cases in here. That is, star spins faster than the gravitational limit. So it's emitting gravitational radiation. So it's above all the interesting frequencies. In this case, spinning the star spins fast, but not so fast, so it doesn't have gravitational radiation emission, but it has a strong field through dynamo process. The third process is it's just so slowly spinning that it doesn't have anything to do with the gravitational radiation. It doesn't have any dynamo mechanism working. It have a strong, not so strong field, and the time scale will be long. So you essentially have these three populations, and one gamma ray burst with relatively high luminosity. One will be a gamma ray burst population with relatively comparable but slightly less luminosity but longer time scale. The third one, gamma ray burst, which might be more relevant to supernova time event. So if you combine this idea, then we essentially can define three classes. One is super gamma ray burst, essentially rotating fastest, and will be that is going to be rotating slightly less, and then there will be weak gamma ray burst, but it will essentially have something to do with the supernova explosion. So this is mostly what I talked about, and I'm skipping something in here. And do I have about a minute or two? Okay. So this is, so I'm just going to finish up with this idea. So gamma ray burst we talked about. So we more or less expect what would happen if the gamma ray bursts are due to millisecond pulsars. But these days, people are talking not only gamma ray burst, but also after gamma ray burst. But after gamma ray bursts disappear at the same locations in the sky, you see optical, radio, and some X-ray signals. So the picture is gamma ray bursts were emitted at the center, and somehow the leftover energy moves out, and there will be more energy coming out at the at larger radii. So if you have a pulse center, what happens is this is not entirely disruptive. Very to have some leftover any energy source at the center. Most of the emission after gamma ray emission stage will be determined by projected during the explosive stage. But if you have a pulsar left over in here, then the explosive energy phase ends, then you will be eventually taken over by the energy injection from the center. That is actually what I mean by afterglows with the millisecond pulsars. So this millisecond pulsar will inject energy in just too little energy coming out. So if you have this kind of millisecond pulsar sitting at the center, what you expect is this, essentially, just right here. So if you have a very fast-spinning millisecond pulsar, initially it will be spun down by gravitational radiation emission. So during that stage, whatever energy comes out from the center will be the time scale, the duration of the event. But after about suddenly the energy injection from millisecond pulsar will sort of go down much faster than t to the, in essence, it's t to the minus 2. So you expect the decrease of luminosity described by a sort of broken power law in time. But if you have a millisecond pulsar which has nothing to do with the gravitational radiation emission, it will essentially remain constant as long as the electromagnetic radiation is interesting for gamma ray burst. That's here. And then after that, it will be broken into t to the minus 2. So have much steeper decrease in luminosity. But millisecond pulsars could do a similar thing in here. So I'll just put on the summary in here. I didn't have much time to cover the supernova connection, but I can summarize it in one sentence. That is, supernova, we've done complicated considerations, but it in essence requires to get rid of the high density environment, at least along the rotational axis or jet axis. That requires jet power of about 10 to the 52. So, isotropic case. So if the jet is very highly collimated, then the supernova will form, and then there will be the compact object at the center. But the envelope of the progenitor star will sit there. But you have to first lift them up out of the along this rotation axis, and then there will be this electromagnetic dipole radiation, just like in black hole picture and neutron star picture along this rotational axis. So this axis has to be cleared if you want to have gamma ray burst. That's actually most severe constraint on the supernova picture, but in most cases, the energy-wise, it's not a problem, but in essence, it has to be seen whether actually that kind of a heavy MHD type jet could be produced right at the time of a supernova collapse. So that's an option so we have to look for. But if it's gamma ray burst, then I think we already found them. But it's unclear whether all supernovae have something to do with gamma ray burst. So I'll just finish right here.